Alright, let's look at a least squares problem. Now this is something I could do in Excel. It's actually, here's Sage Cell, but I could also do it in Desmos. Here are my data, those same data. So let's look at it though in Sage Cell. So what I want to do with these particular data is, let's see, I need to go back here. I'd like to fit it to a quadratic, ax squared plus bx plus c. And the way I made it, I actually know that I won't probably get these exactly right, but I made them so that a was 3, b was equal to -2, and this is weird. And then C is equal to 4. So we should get some answers that are, left justify that. We should get some answers that are, or an answer that's pretty close to that as far as fitting this quadratic. Now, to fit that quadratic, I make a matrix, right, that has a column of x squared in it, and then a column of x, and then a column of 1s, and then that's multiplied by my unknown ABC, and I get this right hand side. So let's look at Sage Cell and Sage Math. So here is x squared. I had 1s, 2s, and 3s. Here's x, and here's my columns of 1 for A, and then here's the right hand side with the data. So to do least squares, I need A transpose. Oh, I don't think I showed A transpose, so we'll toss that in here too. Show A transpose. But notice, once I make the matrices, A transpose, just like it looks, dot transpose. Again, you can go to this to find such things. So I assigned that, and I called it AT, and then I did A transpose times A and A transpose times B, and called those something I thought was reasonable. And then I made my augmented matrix A transpose A with A transpose B, so I put that right hand side on it. And then I did a reduced row echelon form, and we should be able to see then the answer. And then I also showed A transpose, and so forth, and we can look at those. So I hit evaluate, and hopefully that works. Uh-oh, an error. What's it say? Okay, augment. Wow, big error. Attempt to coerce non-integral real number to integer. Ooh. Okay, so these are interesting things you find. So these are decimal, these are integer, and when it went to augment here, it was not happy. So there are some things you can do. If you go back here and look at construction, they use things like ZZ, QQ, CDF, here's QQ. Those are the different fields, so like the integers, rationals, complex numbers, that kind of thing. So let's try, we can try this two different ways. One, since I'm thinking of these as real numbers, let's try doing RR for real. And here we do RR for real, so I'm specifically telling it what kind of matrix this is, what these entries should be thought of. And so let's evaluate, and oh, it was much happier. And so there's our answer as far as our augmented matrix. It's really big here. I got to go to the bottom to scroll over. That was the identity. Now, I could make this smaller, I guess, but here where you see stuff times 10 to the -14th, 10 to the -15th, those are zeros. Okay. Oh, and I can still see the answers here. And you see we got an answer of like 5, negative 10.6, and 11.5. That's a pretty far cry from the 3, negative 2, and 4 that I thought it should be. But we can go check these things, right? So here's Desmos. And the way I can get this to fit that model is if once I have my data, notice they're named X1 and Y1. If I say Y1, so this will do a least squares, instead of saying equals, use a tilde, the little squiggly thing like that, and then AX1 squared, and notice it starts giving me stuff down here, plus BX1, and then plus C. And I'll make this go out a little bit, and so we can see the fit. It looks pretty good there. And notice 5 for A, negative 10.6 for B, and 11.5 for C. That is what we got. And then you can do the same thing here. You can get that least squares fit. If I say I want to edit this, and then I go in here and I say add a trend line, insert trend line. I want a polynomial of degree 2, so that's good. And then I want to show the equation and say OK, and there we go. There's that 5.05, negative 10.6, and 11.5. We're getting the same answer with each and every one of these. Now I want to go up here and just try something. Instead of RR, let's try it with the rationals. So it'll be fractions, and I don't know how it'll do. We'll say evaluate, and oh wow, nice, right? So it did the fractions, and we get 101 over 20, which is 10.05. We get negative 53 over 5, which is negative 10.6. Oh, I said 10.05, 5.05 up here. And then 23 over 2, which is 11.5. And there are our matrices. So here is A, here is A transpose, and then A transpose times A, we get a nice square matrix, and it is symmetric. And then A transpose times B, we get the 3 by 1 there. And so we solved that equation where we had this matrix with that one. And so our solution is, what is our solution? Where was it? Oh, back here. And I can always get at that solution again up here using some of these matrix things. So if I show our answer was in C, it was the last column, so that's 0, 1, 2, 3, column 3. And again back here, matrix from columns, so that's dot like that. Whoops, there we go. I'll do a Control C to copy and show. I want C, and then I'll do a Control V to paste, matrix from columns, and I just want column 3. And so we will show that. I need another parenthesis, so evaluate. And so there's my answer. Right, and I can look at that answer in decimal form again, so I can always get, even though these are fractions in rational form, if I do a dot n and parentheses like that, it should show me in decimals. And there we go, in decimals. And those are a little bit nicer decimals now. And if I worked at it, I could get it to only show me to say 2 decimal places or something like that. But but I can get it that way. If once in a while it may give you a fraction, but sometimes you get a fraction like 1,000,006 over 822,007, and so I have no idea what that is, right? And so you want to go to this numerical form. Okay, but there we go. I put in the two matrices, and I do the multiplying by the transpose, and get the two sides. I can augment them. Now I could also solve this system back here with A transpose A and A transpose B. We're doing it by reduced row echelon form, but I think try to do this without looking here. If I take A transpose A and do a backslash A transpose B, I believe that solves the matrix equation A transpose A X equals A transpose B. So let's show and see what happens. And we do. So that gave us the solution. So I can just use the ability to solve a matrix this way, and I guess to go even one further, right? This is the least efficient thing to do, but I could say A transpose A inverse and times A transpose B, the right hand side there, and again I should get the answer, but this is the worst way to go, is actually using the inverse, stating the inverse this way. So let's see what happens. Maybe fine. Yeah, it's fine in this case. We get the same answer. So we have these three ways to get the answer. I can do the reduced row echelon form of the augmented matrix. I can use the Sage Math linear solution formula thing here, where you just do the right hand side matrix, left hand side matrix, and a backslash. Or I could actually do multiplying the right hand side by the inverse of the matrix on the left hand side. But again, that's the worst way to go. One of these other two is probably the better thing to do. Okay, and that is least squares in Sage Math. I think pretty straightforward. And again, here I ended up using the QQ for rationals, but the RR works fine. It sounds maybe like you're laughing or something, or a seal. But sometimes you might need to. And we see that in things like Desmos or spreadsheet, we do get those same answers. So we must be doing something right.